So this is a short video that goes into another facet of energy in chemical reactions, and that is this concept of enthalpy. So it is definitely one of the key words in this video. So I'll define enthalpy, talk a little bit about enthalpy and how we can sort of recognize it or try to begin to understand what it implies. We'll look at enthalpy diagrams, and then we'll look at thermochemical equations, which contain typically are a balanced chemical equation with an enthalpy term included as part of the equation. So I'll show you how those work. So let's get started. But first, just to quickly remind you a little bit about what we've already looked at. So we talk about changes in energy. And so we want to calculate a delta E. We need to know the final energy of the system or surroundings. We need to know the initial energy of the system or surroundings. And so change is simply a subtraction. So that's pretty straightforward. But don't forget again, what are the system and the surroundings? System, as this diagram shows, would be the reactants and products in the Erlenmeyer flask that are reacting. And so the surroundings are everything else. For some reason, this flask is in a box, but anyways, the box and anything outside of the box are considered the surroundings. And so there's two different ways that energy can move. Energy can move out of the system, as the red arrow indicates, and that's going to give us a negative sign for the energy. And that negative sign for the energy is a negative sign for the energy of the system, always. So the frame of reference is the system. So if the system loses energy, that's a negative sign. If the system gains energy, the blue arrow indicates that. So energy is added to the system, or the system absorbs energy, and that's going to be a positive sign for that energy. So increased energy, positive sign. Decreased energy, negative sign. For the system only. So the frame of reference is always the system. All right. So enthalpy defined then. So enthalpy H is a measure of the total internal energy of a given system. Again, we're looking at the system here. Now, it's actually defined by this equation, H equals U plus PV, U being internal energy, pressure and volume being P and V. But here's the thing. You cannot measure directly enthalpy. So we don't, as I mentioned, we don't have some sort of measuring device that allows us to directly get a measure of the internal energy. So we don't worry about measuring the internal energy directly. We look at changes in enthalpy, delta H. So delta H is much more common. This is what you're going to see a lot more, is delta H, or change in enthalpy. Now, we plug that into some equations and we fool around with them, we manipulate them a lot, and we get this term, which, again, you don't have to worry about too much, but it's useful to kind of appreciate what it means. And what it means is this: delta H equals delta Q, or the change in heat at constant pressure and volume. Most experiments are carried out at constant pressure and volume. That is an open system, that's constant pressure, and again, a volume of, for example, liquid in solution, and that would be constant volume. If it's a gas experiment, the volume is going to be constant. So very often the conditions are constant pressure and volume. Therefore, we can say that change in enthalpy equals a change in heat. And so you commonly see enthalpy referred to as heat energy. So if you see someone talking about, or hear someone talking about an increase in heat energy, what they're really saying is an increase in delta H. And this is often then shortened to heat, because delta H equals delta Q, enthalpy equals heat. So just to make you aware, if I use those terms, or if you see those terms, we're still talking about enthalpy, delta H, change in enthalpy. All right, now entropy in the glass. So it's pretty hard to visualize this, the internal energy of the glass. Does this glass contain internal energy? And I think we've already sort of ascertained that it does. And there's two components we want to be able to recognize. So the first one would be the kinetic energy of the molecules. And so in our glass, here's our sample of glass, and here's a molecule, and it's moving. Here's another molecule, and it's moving. It's so that translational kinetic energy of all those water particles, or sorry, not translation, vibrational and rotational. So there is definitely some kinetic energy, that energy of movement. So we can't see that in a glass of water, but we know it's there because the temperature is fairly high. What's the second component of energy? Well, there's chemical potential energy. And that chemical potential energy comes from two sources. And one source, again, is if this is a water molecule, is another water molecule. Well, what is that between them? What is this between those water molecules? That is intermolecular forces. So there's some energy associated with the intermolecular forces, potential energy. Remember, if you want to break those, you have to apply energy. So if they form, they're going to release energy. So intermolecular forces contain the potential energy. And then, of course, as you realize, we have those bonds, which if we can have a reaction take place, the covalent bonds will have an associated chemical potential energy. That's not so always in a glass of water sitting there. Certainly those intermolecular forces are. And so we can look at enthalpy now in this regard, that internal energy, something I called thermal energy before, essentially the same thing, kinetic energy and chemical potential energy. All right, so there's different types or are associated enthalpy changes. So here's a sort of generic form, delta H X, and I'm going to explain this in a second. But so the X means the different types. So delta obviously means change in. H is our heat energy. There's that term again, not called enthalpy, called heat energy, still enthalpy. This is the intro and standard conditions. And for thermodynamics, it's SATP typically. So that is 298 Kelvin and 100 kilopascals. Okay, so that's SATP. That can change if you're looking at gases and stuff, but that typically would not be standard conditions. It all depends on what's going on. Then X is going to be some type of change. And so what are the different types of change? Well, there's all kinds of them. And so here's a few examples. So standard enthalpy of a reaction. Here's the important bit. Delta H naught is that's what tells us it's standard. Again, that standard conditions at SATP. So when it's just a given reaction, it's Rxn is the subscript. And so this is the enthalpy of a reaction under standard conditions. So that's SATP, and all the reactants are in their standard states. So you would not have a standard enthalpy of a reaction for the combustion of solid propane, because the standard state of propane is liquid. Okay, so the reactants are in their standard states. Standard enthalpy formation. We get into this in a little while. The subscript F tells us it's an enthalpy of formation. Standard enthalpy of formation is defined as the enthalpy change associated with the formation of 1 mole of a compound from elements in their standard state. And so we'll see, like I said, we'll talk more about that later, but that's a standard measure of an enthalpy. They don't all have to be standard, so enthalpy reaction, again, delta H Rxn. So a reaction under non-standard conditions, again, that could be a reaction with gaseous water vapor, which is not standard state for water. Enthalpy of combustion, pretty obvious, delta Hc. So again, any combustion reaction, they don't have to take place under standard conditions. So you can have simple enthalpies of combustion. And an enthalpy of vaporization, the amount of enthalpy associated with something changing from the liquid to the gaseous state. And again, if that's water, it could be a standard enthalpy of vaporization, but if it's something that's not normally a liquid, it's just an enthalpy of vaporization. And there's more. There's lots more you could probably think about yourselves, but these are just a few. These are fairly common ones. You might see those. Principally, heat transfer then comes into it. Remember, we talked about heat transfer as transfer down a gradient. But what we want to look at, and we use this in our enthalpy calculations, is when what we want to recognize is the signs here. And again, if we have heat transferring into the system from the surroundings, as is shown here on the left, so that heat is absorbed by the system. Again, the system is always a frame of reference. Delta H is greater than 0 or positive. If you have a delta H that is positive, you have an endothermic process. So conversely, if delta H is less than 0, delta H is negative. It's exothermic, and exothermic reactions, where we all know this, the system liberates heat or produces heat, and that heat is released into the surroundings. You can feel that heat being released in the surroundings in a lot of instances. Standing next to a fire, you feel that enthalpy of delta H of the reaction in terms of the heat being released into the atmosphere that you can feel on your hands or wherever. Okay, so heat transfer has a place in enthalpy as well. Now, enthalpy diagrams is one way to show standard delta H's or enthalpies. So a couple things to notice. The scale is enthalpy. This isn't delta H. This is just an enthalpy scale. You never see values for enthalpy. There are never absolute values for enthalpy because we cannot determine them. So really, this is just a schematic or a diagrammatic. And so shown here are both exothermic and endothermic. So combustion of methane, CH4 plus oxygen, yields carbon dioxide and water. So that's complete combustion. Reactants down to products. So this arrow pointing down. Exothermic. The enthalpy of the reactants is greater than the enthalpy of the product, so energy must have been released. Heat, energy out. Exothermic. The opposite then would be endothermic, where you have reactants solid water being changed to liquid water, so the melting of ice, for example. And again, to melt that solid, heat has to be added to the system. The system absorbs that heat. An ice cube sitting on a fire or on a stovetop, for example. So the stovetop is providing the heat. The heat is absorbed by the solid ice cube, and it is changed into liquid. So that's an endothermic process. In that case, the delta H value would be positive. Okay, and finally I want to talk about thermochemical equations and how we can add an enthalpy term to a chemical equation and therefore give the information that we are after in terms of the energetics, the energy changes in that chemical equation. So again, there's our enthalpy diagram that you've just seen, and so we're going to deal with the exothermic reaction first. That's the red arrow, and so reactants to products. Enthalpy is lower for products, therefore that's an exothermic process. And so to write that as a thermochemical equation, we just write the reactants, mercury, liquid, plus 1/2 O2 gas, yields mercury oxide. And then we simply write the delta H term with the appropriate sign. So delta H equals negative 90.83 kilojoules. Negative, so it's critical you remember the negative sign. Now the other way to write that is to actually include the enthalpy term as part of the equation. And so to do that, we're going to write, again, our reactants and products. And it's exothermic. Energy is released. The other way to look at that is energy is a product of the reaction. So we can write it as a product. Okay? And this is a useful way to express it for some when we get to chemical equilibrium, because it puts the thermochemical term in with the reactants and products, and that can be useful sometimes. So that's an exothermic process. On the other hand, for an endothermic process, so this is basically the reaction in the opposite direction, we're going to write it in a similar fashion, but now we're looking at the blue arrow and we're going up from our reactants. So our reactants here are H2O solid, and they yield liquid mercury and oxygen. and the delta H term is positive because it's endothermic. Energy is required, so positive 90.83 kilojoules. Or we can write it with the enthalpy term as part of the thermochemical equation. It's part of the equation, and again, since it's endothermic, we look at that energy, that heat energy being required to drive the reaction, so therefore it is a reactant. And so we would typically state that first, and then write the rest of the equation. So there's my other reactant, energy plus my mercury oxide yields my products, liquid mercury and oxygen gas. And so that's how you deal with an endothermic process in terms of putting the thermochemical term in part of the reaction. It's a reactant in this case. So that's a quick little summary of enthalpy and showing you a few options for express or communicating enthalpy, enthalpy diagrams, and thermochemical equations with enthalpy. And that concludes this video.